Hey everyone, welcome to the very last video of the semester where we're going to talk about amide chemistry, where we're rounding out our carbonyl compounds portion of this unit. So we talked about this multiple times before, where we have these carbonyl compounds that have different functional groups on them. As I said before, we're going to take the aldehyde and ketone. You can know what they are, but we're pretty much ignoring them. For this semester, we just don't have time. And then we've already talked about carboxylic acids, acyl chlorides, and esters. So all that's left is to talk about the amide, and that's what we'll be doing today. So just as a refresher, this will help explain some of the reactivity patterns that we're going to see in a moment. This is the scale of reactivity of our different carbonyl functional groups, where something like our acyl chloride down at this end is the absolute most reactive thing because it has a really great leaving group and a super strong electrophilic carbon center. And then we go to ketones and aldehydes, which again, we're ignoring this semester. Carboxylic acids and esters are fairly similar in their reactivity, and amides are on the very end as far as being the least reactive of our carbonyl functional groups. Part of that has to do with the resonance stabilization that can occur with this pair of electrons that I've drawn in here, where the nitrogen can donate these electrons in like so and push a negative charge up onto that oxygen atom, right? Because nitrogen doesn't mind being positively charged, it's not so electronegative, it doesn't mind sharing its lone pair of electrons with that oxygen. And that helps make the carbonyl less electrophilic. So that means we're not going to be as easily able to do the reactions that we've seen in the past. If we take an amide and expose it to something like Cl-, which is a pretty good nucleophile, we could get something like this acyl chloride as a product of that reaction. If we took an alcohol, we could substitute the NR group for an RO group and make an ester out of that, or we could use just water instead in a similar process to make a carboxylic acid. But the problem is that none of these reactions work. Well, we tried. They don't work as written, at least. So if we wanted to get them to work, we're going to have to force them a little bit. So they won't work unless we add heat and acid. We're going to need a little bit of catalytic acid to help make the carbonyl carbon a little bit more electrophilic. We saw that in the case of the esters already. So this is something that you should be familiar with from having learned it in those last rounds of reactions. So the reactions that we'll be focusing on for today for amides will be this one. We'll draw the mechanism for this on the next slide, where we're going to turn an amide into an ester. And then because it's essentially the exact same mechanism, just using water instead of an alcohol, we'll do the carboxylic acid product as well. You will not be responsible for any reactions that turn amides into acyl chlorides. Don't worry about that for this course. So let's look at that mechanism, shall we? Here's what we start off with. We're going to take an amide that has a methyl group on this side and another methyl group on that side. We're going to expose it to this isopropyl alcohol, right, in blue there. And it's under these acidic conditions here, and we're also employing a little bit of heat, right? So if you're seeing that acid catalyst and the hint about heat, it means we're probably transforming an amide into either an ester or a carboxylic acid. And then you just need to interrogate what is the structure of your nucleophile to decide if it's going to be a carboxylic acid or an ester. And in this case, since we have an alcohol nucleophile, we end up with this ester group here in our product. So let's see how we get there, shall we? So the first thing that needs to be done is to protonate our carbonyl oxygen, and we're going to use our acid catalyst to do that. I'm just going to draw HCl out again so that we can see that bond, so we can show it breaking. We're going to use the electrons from that carbonyl oxygen. Remember that the carbonyl oxygen is pumped up in electron density because of the resonance donating capability of our amide. So the oxygen reaches out, picks up a proton, and then we go ahead and kick out that chlorine, just as we've done many, many times in our acid-base unit. And then we'll get to something that looks like this. Now that we've improved the electrophilicity of our carbonyl carbon right down here, we can have our nucleophile water come in and attack it, right? Because neutral alcohols and water are in that classification from our third unit of weak nucleophiles. So this weak nucleophile is just going to use its lone pair of electrons to come in, attack at that carbonyl carbon, break the pi bond, and push those electrons up onto our oxygen. Then we're going to form a tetrahedral intermediate that looks something like this. Check your charge balance here. We started with a neutrally charged alcohol and a positively charged carbonyl. We put them together, we still have one positive charge overall, but we don't really like that positive charge, so we're going to have to get rid of it through a couple of proton transfers. We first want to pull that proton off of our oxygen, and then we need to turn something into a good leaving group, so we'll have to do a little bit more protonation after. So what can you use as the base? You can either use our alcohol, which is a decent base. You're welcome to use the chloride anion as well. That's what I'm going to use here. As long as you use an acceptable base and you draw the arrows correctly, I don't mind which one you use. So we're going to pull off that proton, and then we'll get to another tetrahedral intermediate that looks like this. And now we just need to think about a leaving group, right? Based on the fact that we know what our product is, we know the nitrogen has to leave. So we want to turn that nitrogen into an even better leaving group. It cannot leave right now, because if it was to leave right now, it would leave as NH-, and that's no good because that is a super duper strong base. And that made it a bad leaving group to start with. But also, we're under these acidic conditions, so it's just not going to happen. What will happen instead is the nitrogen will be protonated first using our acid catalyst, and then it will be a good leaving group to be able to be kicked out without making any strong bases. Remember, we don't want to make strong bases in an acidic solution or vice versa. No, 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 that is not how we do it in organic chemistry. So we're going to take our newly reformed HCl, right, because that was a byproduct of this step prior. And we're going to use the lone pair on nitrogen to pick up that proton. And don't forget to break your second bond to that chlorine atom. And then we get to yet another tetrahedral intermediate that looks like this. And now we're pretty close, right? We just need to kick out that leaving group and reform our carbonyl. So that will be our next step. What do we want to use to reform our carbonyl? We have a couple of different options here. We need an atom that's adjacent to our leaving group that has, a bit of lone pair electron density that we can use to help push that leaving group out and make it leave. And so we talked a little bit about this in one of the previous lectures. Go back if it still doesn't feel super familiar or easy. When we're talking about reforming a carbonyl, we'd much rather pick an OH group than an OR group, because we can easily pull off hydrogens to neutralize a positive charge. We can't do that with carbons. So it would be a little bit annoying to have to do with a carbon-based group. We're just going to avoid that. We'll use the one that's much easier to do, and that is the one that has the hydrogen attached. So we want to pick this top oxygen right here, use its lone pair electrons to fall back down, reforming that pi bond, and then we're going to kick out our nitrogen as a good leaving group, like so. And then we'll get to here, where in the process of this, we've kicked out methylamine and reformed our carbonyl to give us something that looks like this. But that carbonyl still has that hydrogen bonded to it, so we're definitely not finished yet. But now it looks a whole lot more like the ester product that we know we were trying to make, right? So only one last step to do, and that is to use some kind of an appropriate base to pull off that proton and get us to our final product. So I'm going to use chlorine minus again, partly because it's the easiest thing to draw, but also partly because that helps us reform our catalyst, and that feels sort of like a nice closure to the reaction as well. So there we go, we form our ester, we reform the HCl catalyst. So let's just talk through that again really quickly while we go and label the steps. In the first step, we use the carbonyl oxygen, which is the most basic atom in our whole molecule here, to do an acid-base reaction first to make our carbonyl carbon a better electrophile. Next, we have our weak nucleophile of this isopropyl alcohol come in and attack at our carbonyl carbon. So this is a nucleophilic attack. Then we have to do some proton transfers to make sure that our groups are, as neutrally charged as possible and happy. So we do an acid-base reaction here to pull the proton off of our newly installed nucleophile. And then we do another acid-base reaction over here to start forming our good leaving group. Then we do this step where we push out that nitrogen. That's the leaving group leaving step. You may also hear me call this elimination. Either way. And then last but not least, another acid-base proton transfer there to help you finalize and get to the end product. So this mechanism you'll be responsible for, and this same type of mechanism, but with water here instead of an alcohol for your nucleophile, you'll be held accountable for on the exam and the final. So you may be saying, Grace, we've done a whole bunch of different carbonyl reactions and they're fine, but what would I care about amides? Why would that be interesting to me at all? Well, the cool thing about amides is that you are amides. I already said that your chemistry, your molecules, your amides. Protein is a bunch of amides. So you have probably heard the term protein as it comes to like nutrition or thinking about like muscles, right? You may have also heard it in a more scientific context referred to as peptides. Right? Peptides are proteins. Proteins and peptides are all made up of amino acids. So a couple of those terms maybe sound familiar to you, but why are these things called amino acids after all? Well, when we have a molecule that looks something like this, I'll scoot it up a little bit here. This is the basic formula for our standard amino acid. And so an amino acid, this is just a little tiny bit of general nomenclature. You don't necessarily need to know this, but the nitrogen-based group here is called an amine, hence the amino. And then if you look over here, hopefully this looks familiar. What I've circled there in blue is a carboxylic acid. So it's amino acids. And you may already be aware, if you've taken any biology before, that amino acids are an essential basic building block to life. So I'm not going to go through all of the amino acids because you certainly don't need to know those for this class, but just to look at a couple of fun examples. This first one over here, depending on what the R group, right, that side chain is, you get a different amino acid that has different properties, right? So this one with the sort of CH2 here and an OH on it is called serine. If instead of an oxygen, you have exactly the same structure, but with a sulfur instead, you call that cysteine. And that is going to have slightly different properties than the version with oxygen in. And of course, there's a lot of variety to the structures. I just picked a couple of relatively simple looking ones. When we have this kind of longer carbon-based group here instead, we call that isoleucine. So you may have had to memorize, some arbitrary number of amino acids for biology classes before, and I'm definitely not going to make you do that here, but just to know that there's a bit of variety to the structure and what they can do in your body. And so I'm giving this introduction on amino acids, right? But you might be looking at yourself, you might be looking at your screen and thinking, Grace, wait a minute. These amino acids, they're not even amides, right? And I would say, yeah, they're not. They're not amides. Well, not yet, they're not. If we look at the difference in an amino acid and an amide, right, it's all to do with where that nitrogen group is and a little bit to do with where the R group is. If we have an amino acid, we have the amine group here. The reason we can call it amine or amino is because it's not immediately adjacent to our carboxylic acid, right? There's this carbon, this sort of CH with an R group on it that's in the middle that kind of breaks it up. Whereas if we have an amide, the nitrogen group is right next to the carbonyl or carboxylic acid. It doesn't necessarily have to have an OH here, but this bond right here between the two of them, where the carbonyl is directly bonded to the nitrogen, that is what makes an amide, that specific bond. So no, amino acids are not the same thing as amides, but when we combine amino acids together to make things like polypeptides and proteins, if we take many of these amino acids and put them together in a condensation polymerization reaction, what we get is a polymer that looks like this, right? And if we examine the structure of this polymer, I think what you'll be able to find here are a couple of places where we have a carbonyl that's bonded directly to a nitrogen. There's one there, there's one there, here, and the pattern will keep continuing on either side here. You can't see it, but all of those purple highlighted bonds, those are the connection between an amide, right? These in biology are more commonly referred to as peptide bonds, but in reality, they're esters, just two different names based on two different disciplines. If we turn this amino acid into this polymer, we might call this a polyamide or a polypeptide. And so, depending on what the nature of those R groups is, then this polypeptide, this protein chain, has a bunch of different properties to it. It can fold and twist around itself in a bunch of different ways that give it the different functions that different proteins and peptides have in the human body, in animal bodies, anywhere. So why did I say condensation polymerization? Well, that has to do with what is the byproduct of it. And if we say condensation, you might think of, a glass of cold water on a hot day gets a bunch of condensation on the outside. And what is that? That's just water coming out of the atmosphere. So when we do a condensation reaction, that means we're getting water coming out of the reaction. And if you take a look at the structure of our polyamide and our amino acid that we started with, you can kind of see where that water comes from, right? If we look here, we had an OH group on one side of our monomer unit, but when we put it into the polymer, there's no OH groups anywhere here. So that's gone. That's NHO. And then if we look at these nitrogen atoms in the polymer, right, it had two hydrogens here to start with, but it only retains one of them after the polymerization reaction ends. I forgot to draw them in, but now there they are. So that means that one of these hydrogens must have been lost in the polymerization reaction as well. So if we tally that up, we've lost a total of 2 H's and 1 O, which means we made water and we condensed water as a byproduct of this reaction. So we're not going to talk too much about the specific conditions that would go into polymerizing these in, say, the laboratory. There's a bunch of different ways that biologists and biochemists can make these peptides for study in, if they were trying to do things with medicines, animal-related studies, even chemistry when they're not really planning on putting it into a living system. But we don't have a lot of time to talk about those. So we won't focus on what these reaction conditions are. You should just be able to identify amino acids by sight. And again, none of the names, just to know that it's an amino acid and that they form peptide bonds, which are really amides. So that's just a little bit about what amides are cool for in literally your everyday life. They are a part of your body. But another thing that we're probably interested in as far as amides go is getting a little bit of practice in so we're ready for exam 4, which is coming up pretty shortly. So if we go ahead and work through some of these, I've sprinkled in a bunch of amide-based reactions with some that aren't amide-based. So we'll have to do a little bit of checking to see what could possibly be happening in each reaction. This will be a little bit more like what you would see on the exam. It's just a mix of predict the product questions that aren't necessarily categorized in any way. You have to decide what's going to happen. Let's start with this first one. Pause the video here and make a prediction about the outcome of this reaction. Here we see an acyl chloride and we are treating it with something. So we're not starting with an amide, so this must not be any of the reactions that we learned today. This must be something else from earlier in the unit. If we have an acyl chloride, we know that's a really strong electrophile, so we just need to look at our nucleophile and see what that is. Our nucleophile here is something with sodium, so we know that has a positive charge, and then this NH2 we know has to have a negative charge, so that is going to be a strong nucleophile. That's going to create our tetrahedral intermediate when it attacks. And then we have to ask ourselves, which one is the group that we want to kick out at the end, which is our better leaving group between chlorine and NH2, both with negative charges. And hopefully this rings a bell from when we talked about these in kind of the first day of carboxylic acid derivatives reactions. Chloride is always going to be the best leaving group that we can get. So it's going to go, and that means we're going to have this chloride replaced with an NH2 group instead. So this wasn't a reaction of an amide, but it's a reaction that formed an amide. So this is like an amide synthesis reaction. How'd that go? Did you get it right? Let's try this next one. Now we are starting with an amide, so we're probably going to be doing one of the reactions that we started off with today. If we identify what our nucleophile and conditions are, we can see that we have something up here. It's a little bit weird to tell because it's kind of drawn out funny, but that has got an OH group on it, so it is an alcohol. And it looks like we are under acid catalyzed conditions with a little bit of heat. So this means that we're going to actually be able to attack this weak electrophile because we've given the reaction a little bit extra energy, a little bit of catalysis to help let that occur. So because this reaction is happening under acid catalysis and with a little bit of heat, we're giving it more energy and ability for this weak nucleophile to attack our weak electrophile. We're making the reaction easier to happen. And that means that we're going to put this part of our nucleophile onto the carbonyl and displace the NH2 group. Again, this hydrogen is part of the mechanism there, but it gets removed in proton transfers, so we don't need it in our final product. You're welcome to always draw out these mechanisms to help you predict the products if that is the best way for your brain, but you absolutely do not have to. That means our product is going to look something like this, where we retain our carbonyl, but instead of that NH2, we then put an O and a CH3 group on it instead. So this is turning an amide into an ester, just like we practiced earlier today. Let's try this next one. Pause the video here and make a prediction of what you think will happen. We've got another amide to start, so this is probably something from today's lecture. That is going to be our weak electrophile. And then we'll see what we're going to treat it with. Looks like we have another Na, so we know that that is just something with a positive charge. And whatever's next to it, Cl-. And hopefully it feels pretty familiar to see a halogen like this with a negative charge as our nucleophile. And so it's a pretty good nucleophile. But at the same time, if we think about what happened in our first example, chlorine is also a really good leaving group. So even if it's a good nucleophile, it's also a good leaving group, which means that even if this chlorine was to go in and attack at our carbonyl and make a tetrahedral intermediate, it would always be the thing to leave. It's always going to have a weaker bond to carbon than nitrogen does. And so that means that nothing is going to happen with this nitrogen. It's just not a good enough leaving group. Additionally, we're not under these conditions like we had in the previous example where we have an acid catalyst and heat. There's just nothing down here. And that means that we're not forcing this reaction to work. And if we're not forcing it to work and it doesn't want to work on its own, it is not going to work. So we will get something like NR, no reaction, or you could redraw this starting material if you so desire. How did that one go? Did you get it? Let's try a couple more. If we have something that looks like this, this is another ester, right? So instead of making an ester this time, we're treating it with something else. So let's see what that something else is. We have another Na here, which means that whatever's on the other side of it, nitrogen, must be negatively charged. So we can bring that NH2 nucleophile in, have it attack at our electrophilic carbonyl center, and then we have to ask ourselves which one is the better leaving group between OCH3 with a negative charge and NH2 with a negative charge. Go back to that ranking of leaving group ability that we talked about a couple lectures ago if this still doesn't feel familiar. But the oxygen being more electronegative is going to be better able to stabilize a negative charge. So that is our better leaving group in this case. And that means that we're going to go ahead and displace that OCH3 with our NH2, and that will give us a product that looks like this, where we've made another amide. Okay, how'd that one go? Hopefully, they're getting a little bit more easy and comfortable to recognize. Let's look at this next one. Here we have another acyl chloride and NaOH. Okay, so there's literally no nitrogen anywhere in this, which means that we're not going to be making an amide, but we're going to be making something else perhaps. So let's take a look. If we have this acyl chloride, we know that that chloride is a good leaving group, so pretty much anything else that we could bring in is going to be a better nucleophile and not want to leave after it attacks. Let's examine what we have here. We have sodium with a positive charge, meaning that this is OH minus. So that makes me think that we are going to go ahead and create a 5-membered ring that has a carboxylic acid on it. So not too bad, right? Let's take a look at just one more. And if you've been looking at sort of the caliber of all of these ones that we've had to start with, it looks like there's an awful lot more going on in this one, doesn't it? And you would be right to be a little bit wary of this because look, we've got stereochemistry, we've got this ring with a bunch of nitrogens in it. So what these are amino acids. So these are a couple of specific amino acids, and we're basically just going to put them together. Again, you don't need to know the mechanism of how this works. You just need to be able to predict the product of when they come together. You basically need to kick out water. This is the way I like to do this, is that if you can just find the water on your given molecules, you circle water, and then you redraw everything else without what you've circled in, and there's your product. So we're going to take this OH is going to go, and then we're going to take one of these hydrogens away. So I'm just going to circle the 2, and that's H2O. So if we redraw exactly what we had before, and then omit that water that we condensed away, we'll have our product. So there you have it. We've made a little 2 amino acid chain where we linked one amino acid to the other amino acid using our favorite new kind of bond, a peptide bond. And you may be wondering a little bit about the stereochemistry here. I'm not going to quiz you on the stereochemistry of amino acids, so don't worry about it too much. But I had to flip this one to a wedge because I needed to turn the molecule over to keep my bond angles looking nice. If stereochemistry kind of scares you still, I would recommend going back and reviewing that before the final, but you will not need it for this type of question on exam 4. And as a last minute thought about this reaction, I mentioned that these have specific names, which you don't need to know, but this group down here on our amino acid makes this a histidine molecule, which is labeled H in its abbreviations. And this is one that we saw from the previous slides as well. This is isoleucine, which is abbreviated I. So when you put the 2 together, you can say hi. Hi to a small amino acid chain that we've just built using chemistry. And we'll probably also want to say hello to a few things that we're going to review and practice before the exam. You want to be able to know how to convert amides to either esters or carboxylic acids and be familiar with that mechanism that we just learned. And then if that all feels good, this is the last of our content. So all you need to do is get ready for our upcoming exams. Look forward to getting ready for exam 4. That's next week. It's coming up. So if you have any questions, be sure to reach out. And then once you are feeling okay about that, it's time to start looking forward to the final. I know finals week is probably going to be crazy, but I believe in you. You can do it. Reach out for help as you need. And then when you're done thinking about the final, you get to look ahead to the end of the semester. It's been a crazy one, but I'm so proud of y'all for getting this far through it and hanging in there with me through all of this chemistry. And keep hanging in there, especially as the stress ramps up, like I said, during finals week. But let me know how I can help you with Chem 210 stuff as we approach this time of the year. If you have questions, go ahead and leave a comment here, post some comments in the discussion forum, or you can send me an email or stop by office hours. Just a quick reminder, if my office hours don't work for you, just send me an email and we can set up some separate office hours so that you can get your questions answered and get the help that you need. But until that time, everybody stay safe out there and take care.